at least before the setup time of this flip-flop. So this is the sort of time interval of the setup time. So if the signal changes like here or something, then it's not stable. So the flip-flop may have a wrong behavior if the input changes here. Like we can't predict what the output will be in that case. But here it's shown that like the data changes to 1, but it becomes stable before the setup time starts. So then it will be stable. Uh, so that's the setup time. And the hold time is so even so we give the input, but you can't like release the input. Like the input can't change immediately after this as well. Like it has to be stable some amount of time after the clock edge as well, and that is the hold time. So here you can see this T input is 1 all throughout here, and it only changes here. So if it changes in the middle again, like the output can be unstable. It might not even be 0 1, can be something in the middle. So when this kind of thing happens, like it goes out of the behavior that we know about digital circuits, and it becomes unpredictable. So we don't want that. So that's why setup time and hold time are important. Uh, and the next definition is the clock to Q delay. So this is the time where previously we talked about the input, right? Clock to Q delay is like after the clock edge, the our input D doesn't get to Q immediately. So there is some delay after the clock edge before like this output Q changes. So it doesn't change immediately like here. So this time until the output changes is called the clock to Q delay. So this is not a sort of condition, it's the sort of natural behavior of the flip-flop. And all of these things, setup time, hold time, and clock to Q delay, are usually fixed values for a flip-flop. But the propagation delay changes with the type of combinational circuit that you have. So I hope you got that. If you have any questions about anything, you can also put in the chat or ask. So because the setup time and hold time are requirements, like the data must be stable within this whole interval. So when we are checking, so this is the main thing that we need to check in timing analysis. So that means with all of these various delays in the circuit, will the input be stable within this time? Because if it's not stable, the circuit won't behave as we expect. So this is how we are going to check that. So these are all the times that I introduced: propagation delay, setup time, hold time, clock to view delay, and T clock is the clock period. So here I have 2 flip-flops. So the same clock is going to both of them. Clock period is the time between 2 clock edges. So here to check the setup. So let's start from the time when, like, at the start of the clock edge. So the input of flip-flop 1 will go to, so this input will be passed to Q of here, and that will take a time of clock to, like it will take the clock to Q delay. Then so this is from the start of the clock edge. Then we have the propagation delay of this combinational circuit, TP up to like until the end of the circuit. And then we get to the input of this flip-flop. So we have to get to this point. So before before this time interval, we can't guarantee that the value of Q is stable because value here is stable because it's still like the and gates are no, the all the gates of the combination logic circuit is still doing its thing, so it's not completely stable yet. So because of that, we can only guarantee that the output is stable after this time. But then it that after then there should also be a time interval, the setup time interval before. So after we reach here, only after setup time, we should reach the input of the next second flip flop. Otherwise, the setup time requirement will fail. So because of that, until the from the start of one clock edge to the next clock edge, we need to so this is the time that we need to have for the circuit to behave correctly. Otherwise, it will fail the setup time requirement. And so this is the time between two clock edges, right? So this should be that's the clock period. So if the clock period is greater or equal to this time, so then our setup time requirement is complete. So I'm not sure whether that was clear. So if we put it another way, so if we have the complete clock period is T clock, and then out of that clock period, TP is taken for propagation delay. Then TCQ is taken for the clock to Q delay. So until the next clock edge, so this is the time left until the next clock edge. So the time left until the next clock edge should be greater than or equal to the setup time. Otherwise, the setup time requirement will fail. So this is basically the same equation as this. So this is the setup time requirement. And the whole time, so you can see that the setup time is this requirement. So if the propagation delay becomes too very high, then this part can be get larger than the clock period. So then the setup time requirement will fail. So usually because like these two things are fixed, the cause of setup time failures is the propagation delay. The whole time requirement is it is sort of the opposite. So it's so we are here we care about what happens after the clock edge. So then we have to think about so after this input reaches here and the clock edge has passed, then at the next clock edge, so again this flip flop will also process some other input, and that will again take TCQ and TP to reach here. So if it reaches here too fast, so previous case, if it's too slow, it won't meet the setup time requirement. Here, if it's too fast, then then the data will change before, like it will change before the end of the whole, because this circuit changes. Because of that, the time from here to be larger than the whole time. So TH is the whole time. Uh, Otherwise, so if the propagation delay is too fast, then we will not get the whole time. Being too fast is a problem we can solve. So setup time violation is the more common thing that we face. Whole time violation is more easier to fix. So I will about how those things are fixed later. Uh, for now, I hope understood uh, like what are each of these requirements and why it's important. Um, so yeah, so these are time violation is when the input does not stabilize by the setup time. And this happens when the proper time violation is when input doesn't remain stable until the whole time. And that happens when the propagation delay is too fast, too small. And these timing violations must be fixed, like when I will show in the when after this, after explaining how to do this in quarters. So it will automatically check for timing violations, like obviously. So this is for a single flip flop. It's going to be really hard for us to do this by hand because there are millions of flip flops in a real FPGA. So the software like Quartus or Vivado will do this automatically for the circuit that we build. And it will give not passing the timing requirement. But so if you ignore that and just go to the FPGA, uh, try to run it on the FPGA, it most likely won't work as you expect because there are instabilities in the input and output. So when you see timing violations, you must fix them before going to run on the FPGA. And also there is another concept associated with this setup time because so you can see that this is the setup time equation. Uh, and normally when we are making sort of digital designs, we want to run it as fast as possible. So because running it fast means you can like it's more efficient. So even with computers, we are trying to increase the frequency of the CPU so that every operation will be fast. But that clock frequency is limited by this equation because we can't make this T clock smaller than this time. Otherwise, we will fail setup time violation. And that is also so because these two things are fixed. So that also depends on the propagation delay of that combinational circuit part. So if that propagation delay is too high, we will have to reduce the clock frequency to keep this equation correct. Yeah, like if this increases, we will have to increase this, and vice versa. So, um, so from because of this, we can like figure out what is the maximum frequency we can run this design because the minimum clock period we can have is this. So the maximum frequency we can run is this frequency. And this is important like for FPGA designs. This is important because like normally the clock is at 50 megahertz or something like that. So then if the design that you have made can't run at 50 megahertz, then you will have to do some changes to make it able to run that because so because that's the clock that is built into the board. So maximum frequency is another important thing associated with timing analysis. So then setup slack is, I included this because this is a word that is used in the timing reports. Setup slack means, so there has to be a bracket here. So setup slack is clock period minus this, or adding all of this time. So this is the time that the minimum clock period we can have. So setup slack means how much time do we have left above the minimum. So if this is positive, that means we can actually increase the frequency because it's not at the minimum limit yet. If this is negative, that's bad because uh, because this has exceeded the clock period, so it won't meet the setup time requirement. So that's it, the maximum frequency. And now I will show you how to do the timing analysis using a bit quite simple design. So this is what I'm going to use. It's a 32-bit adder made using triple carry adder. So you will probably have heard of triple carry adders. You have, I think, if in semester 3 there you might have built this also, the design. If you don't know it, like it's a adder made of combinational logic entirely. Like it's made of a more simple component called full adder. And so here we have this is a 8-bit triple carry adder, and we have sort of cascaded 4 of them together to make a 32-bit adder. And so this operates entirely with combinational logic. And just to demonstrate that, like the timing analysis, and like this could be a part of a larger system. So in a more complex design, normally because we need to do sort of iterative operation, we will store inputs in registers. So register is basically multiple flip-flops so that we can store more bits. So here A and B are in registers. So and the inputs are given to the adder, and the output is again stored in the output register. So in this all happens in one cycle. So in one cycle we can give one A and B, and it will be added, and the output will be stored here. And in the next cycle we can give another different A and B, and it will be also added like that. So this whole 32-bit addition operation happens in one clock cycle. And this is the design that I have. Cascaded sequential adder is, so we have A and B and S and C out. S is the sum. This is the carry out. We are saving the A and B to registers, and then this cascaded RC adder is this is a like combinational adder that is made up of 4 triple carry adders. So I'm not going to explain like system Verilog syntax in this session. So what this generates block, if you haven't seen it before, it's used for like generating multiple modules of the same type. So here, using a for loop, we are generating 4 of the 8-bit adders. Yeah, so that's the circuit. So it's the same thing I explained before. And we will, and yeah, I have a top module. So this is actually something I built for a different purpose. And here I have made a module called adder test, which is used to test, give some inputs to the adder and test it. So it's using a VRAM, and I will go into explaining VRAMs later in the FPGA resources part of this session. So basically what this module does is it will give, at each clock cycle, it will give a new input to the adder and save its output back to the VRAM. And the top module is, I have connected those two together. So this is, I am showing everything in quarters. So in Vivado, these things might be slightly different. I will, if there is a significant difference, I will mention it. Otherwise, like, you can follow a guide to, I think it's not that different to figure out. So I'm setting the this top.sc as the top module. So then in the hierarchy, we can see that we have the cascaded adder, and then like four of the triple carry adders, and each one is composed of 8 full adders. So full adders are for uh, and the adder test module is for testing. And then I will run run compilation to compile this. So when we are doing timing analysis, it will check for these conditions, right? So we have to give what is our what is the frequency that we are planning to use. So then quarters will do the timing analysis relative to that. So we have to, I think in quarters by default, it will take the name of the frequency of the device that we are using. So here I have set the device to D0 nano. But if we want to specify a different one, we have to do it with a constraints file. So if you are using Vivado, you will have to do this anyway, because I think it doesn't select something by default. So you will get like meaningless timing analysis results if you don't make a constraints file. So the constraints file in Quartus, the one has the extension .sdc. In Vivado, it's .xdc. The syntax is not really different. So this highlighted one is the important part of the constraints file. So here we are specifying what's the clock frequency that we are using. So here I have defined a 50 megahertz clock. So we define by the period. So it's the 20 nanosecond period. By default, the unit is nanosecond. And get ports here, it means like for the port name, you have to put the port name of the clock in your design. So this here, it's just name clock. If you have something like clock A, you have to put it as clock A. So in this actual constraints file, I haven't I have actually put 200 megahertz because I want to show a timing violation to you guys. So 200 megahertz means period is 5 nanoseconds. And this part is optional. This one you have to specify if the clock edges are in different places. Like here it's specifying that the positive edge is at 0, negative edge is at 2.5. So if it's like sort of shifted, positive edge at 1, negative edge at 3.5, if there's something weird like that, you can specify it here, but you can also omit this part entirely. And there are some optional things that are so actually other things are more important if you are building more complex systems or going for IC design. So IC design, the timing constraints are like there are much lot more things to consider for IC design. Next, most important thing is this set clock uncertainty. So that means a clock is not always perfect. Like, so it might so if this is a clock, so suppose there are two flip flops. Then because it's going along a wire, maybe the second flip flop will get a little bit delayed clock than the first one, like this. It's a very small compared to like this clock period, but it still can have effect. So, and it also may like it might be unbalanced like this sometimes. So because like it might not be perfect at all times. So if we want to account for that imperfection when doing the timing analysis, we can set a clock uncertainty value here. But for FPGA work, it's not like it doesn't matter too much. And the set input delay and output delay, those matter if you are connecting the FPGA to a different system like a microcontroller maybe using the same clock. This doesn't actually happen often, so input delay and output delay also won't be used much by uh, you if you are only working with one FPGA. So if you are taking in an input from another device that uses the same clock, so we know that the output will be stabilized after the clock edge. So that's the clock to Q delay that we talked about earlier. But because like, so this is our device, let's say it's A. So we are getting an input from the other device synchronized with the same clock. But because it's a different clock, it might have different properties of the flip flop. So the the clock to Q delay of this output to reach here might be different. So that's why we are defining set input delay. You are saying it might be a different delay value for this port that is coming in from the different device. Uh, and output delay is the equivalent for giving output to another device that uses the same clock. So this is only relevant if we are using external devices that use the same clock, like they are all synchronous. It doesn't matter for like taking input using buttons or output to LEDs, that kind of thing. It doesn't matter. So you can ignore timing analysis will give some warnings relevant to these things when we are doing it. But for normal basic designs, it doesn't really matter unless you are working with multiple devices. Even with multiple devices, if you are not sharing a clock, it doesn't matter. So those are the sort of important things in a constraints file. Actually, only the clock will matter for most of your designs. So I have made a 200 megahertz clock, and this file is also added to the project so that it will be considered. So now I will do the compilation. So here it shows like what are the steps in compilation. So timing analysis is one of the steps. So place and route is when you sort of allocate each of the logic components that are used in the design. You are allocating them to different parts of the FPGA. And after you do that, then you connect all of them with, so FPGA has three sort of pre-configurable wiring. And after those things are configured, it does timing analysis. So now we can see in the compilation report, under timing analyzer, you can see that it's red here because there are some warnings. So it will be given here also, like timing requirements not met. It will be given as a warning here. So if you see this, you will have to somehow fix it. So I used a 200 megahertz clock here. So here there are different things under the timing report. So if you want to make sure that the STC file has been taken correctly, you can check this clock. So clock frequency is 200 megahertz. That means it has considered the clock that we have given. Then these three things are like so it has done timing analysis under several different conditions. So the delays that I have mentioned, like it will also change with so they can change with temperature, with many different, like if the voltage changes, it might change. If the temperature changes, it might change. So because of that, it's doing timing analysis under three different conditions. So there are sort of libraries that give, like for this AND gate, the propagation delay is this much under 85 Celsius and this much under 0 Celsius. That's that kind of thing. So it's checking few extremes, because then if it works for extremes, it should work in the middle. So let's check one of these. So if any of these are failing, it's much, good to fix them. So here, setup summary is red, hold summary is not red. So there are no hold violations, but there are setup violations. So setup slack is minus 2.7. So I define slack here. Slack is clock period minus this. So that means this is larger than the clock period. That's why we have a setup time violation. And it has also calculated the Fmax. So you can calculate the Fmax here. So because this is given as slack, like the timing report gives the slack. So you can use this sequence to calculate the Fmax if it's not given here. So in Quartus, it will give you the Fmax directly. In Vivado, it doesn't. It will only give the setup slack. So if you want to calculate Fmax, you will have to do this calculation. So if I check that for this case, 1 hour, so our clock period is 5 minus, and this is also minus 2.75. Uh, yeah, and because this is nanoseconds, this is in gigahertz, I will multiply by 1000. So it's 129. If max is like 129. So this is the same as if we do the calculation. So we put the frequency as like the we gave it as we are operating at 200 megahertz, but this gives that with the current state of the circuit, we can only operate at maximum 129 megahertz. So we can't. So with these conditions, we can't operate at 200 megahertz. So this matters for like larger systems like CPUs or accelerators, because the clock period determines how much work you can do in one time. So here I said that. So here I said that we give A and B in one cycle, and then next cycle we give another A and B. So suppose our clock period is 5 nanoseconds, then to do 100 additions, we will take, yeah, let's take a million additions. To do million addition operations, we will take million nanoseconds means 5 milliseconds. So if if we are limited by this, we have to operate at 129 megahertz. So that means so 7.7 megahertz per 7.7 nanoseconds per cycle. So to do a million additions, it will take 7.7 milliseconds. So that time adds up when you are doing even more. So I took a million, but if it's running continuously, it should be able to do a lot of operations, and eventually the time difference becomes very significant. So that's why the max is so important here. Because if we want to something, because we are using the FPGA to do something faster than we are doing it with the CPU. But if we are limited in the frequency that we are using, maybe we won't be able to do it faster than CPU. So because of that, we have to try to make, like, the goal is to make the clock operating frequency as fast as possible. So how do we fix these timing violations? So when we are fixing, so first thing is we need to find out where this timing violation is happening. So because this circuit is very simple, like this is the only combinational path where this circuit is passing through. So in a real more complicated design, there might be multiple paths. So there might be adder here, subtractor here, and multiplier here. So there might be multiple different optional modules that these might be passing through depending on sort of maybe control system. So if any one of these things is slow, so if the adder and subtract are fast and the multiplier is slow, then the propagation delay will still maximum. We are considering maximum propagation delay for the setup time. So if the maximum delay is too slow, it will still cause a setup time violation. So if there are these sort of multiple paths that your signals might be going, we should have a way to find out which one is causing the problem. So I will show with this one. So to find this, you have to go to the worst case timing paths section. So here, this is the worst case setup time paths. So here it's saying from these paths, like these paths in red, are the ones that are having the worst case timing. So if we take the first one, it starts at A saved in the cascaded sequential ladder, and it goes to C out in the cascaded sequential ladder. So if we try to see what this is. This is the cascaded sequential ladder. And this is A save. This is the register with the input. And C out is the register with the carry out of the output. So it says that the path from the input to the final carry out is the longest one. So this makes sense because like to get the final carry out, you have to go through the like entire adder. So the sum, for example, like you can, so when we are doing addition, so the carry of first bit goes to next bit, then it goes to next bit. Like the carry bit carry calculation has to pass through all of this to get to the output. So it makes sense that it will have the longest path since this is all combinational. And if you want to confirm it, you can do right click and do this report worst case path. And here it will have the data path, so it will show in detail which things it will, which signals it passes through. So it goes from A saved to the output of A saved, then it goes to inside a full ladder. Like so it goes inside a lot of full ladders. So it goes through all of the full ladders. We have 32 of them. So this is the entire path. And finally it goes to the C out. So if you want to confirm the actual path the signal is going, we can do that. In Vivado, there is a more nicer interface, like it will show a visualization of the different blocks and highlight the path between them, but I couldn't find that in Quartus actually. So you can check if you are using Vivado, you can check that to see which path this is going. So here, yeah, all of the failing paths are going through C out. The some there are other paths also that they are not failing the time. So how do we fix these things? So there are several methods, and I will mention two of them that are most commonly used. The easiest one is to make the clock slower. So this is not good if you want to make something that runs efficiently on the FPGA. But it's a quick solution. So this doesn't work at 200 megahertz, right? So, but imagine your FPGA clock is running at 200 megahertz, then you don't have a choice but to use that. But you can use a clock divider to divide the clock signal in half before giving it to your adder module. Then it will be 100 megahertz. So, and because the maximum frequency we got is 128, then it should be able to run without timing violations at 100 megahertz. So basically what we are doing is in this equation, the problem is that this part is larger than this part. So we are increasing T clock so that it will become equal again. So I have implemented a simple clock dividers to show you. So clock divider, you can make it by, so this is doubling the clock period. So what it's basically doing is this is the clock, input clock, and we are updating a counter every time. So we are updating a counter at every clock edge. So at this edge it will be 0, 1, 2, 3, and so on. So then for the output, we use the, so at each clock edge, we output the last bit of this counter. So here the last bit will be 0 because it's 0 at this clock edge. So at the next clock edge is 1. Then at the next clock edge, it will again be 0 because 2 is 1, 0. And the next clock edge, it's 1, like this. So we are outputting the last bit of this. And you can see that it automatically looks like a clock signal again, but it's half of the frequency as before. So it takes an entire clock of the the original clock. So yeah, it's half of the clock frequency. There are probably other methods for clock dividers, but this is a simple one. And if you want to divide it again, you can pass it through another cycle. Like you can feed this into another clock divider module that again does the same thing, and it will come out like this. So yeah, that's the simple clock divider. And in this cascaded clock div sequential ladder, I have, in addition to the other part, I have added this clock divider module, and given this div clock uh, input into the, like it, I have used this for saving the inputs and out instead of the input clock. Div clock is divided by 2. So if we use this one instead of the normal sequential ladder, I will put this as the module used for the adder module. So these all, I have used the same interface for all of this, so I can just swap them out. Like the inputs and outputs are same in both of them. So this is already the top module. I haven't changed that, so I can just run compilation. So here, if we check the warnings, it doesn't say timing requirements not met. So the timing requirements are okay. And if we go to the compilation report, so this red is still for, that is for the unconstrained path because we didn't put an input delay or output delay. But for FPGA designs, you are not using external device, you can just ignore that. Uh, in the timing analysis. So these three timing analysis reports don't have the red anymore. So that means the timing has passed. And if you look at the setup summary, now the slack is positive. That means no setup violation and no hold violation. So for any of this, there are no violations. And if you look at the Fmax, so also like the clock is still, the clock that we are giving as input is still 200 megahertz. But now because we have used the clock divider to give the input, we don't have setup violations, and the Fmax is also doubled. This is because so previously we had 129. So that means it will work with if we give an input clock of double of that, so 258. If we got to give a 258 clock, it will be divided to 129 before our module, so that it will still work. So that's why this has a different Fmax now. So, but this is like this is an easy solution, but it's not a good solution because even though we can operate correctly, like our frequency is still down to like 100 megahertz instead of 200. So the better solution, if you want to maintain the speed, is to break the highest combinational delay path into several sections and insert registers in between them. So this is like pipelining. And I will show an example. So sort of a generic circuit. So this is sort of circuit we have. There's a flip-flop input with the input, and there's a flip-flop to capture the output, and there's a long combinational path between them. So instead of doing this all in one combination circuit, we are breaking the same thing into, so here I have broken it into three circuits that, like, if we connect C1, C2, C3 without these registers, it will again give you this long path. But instead of doing that, we have connected them with flip-flops or registers between them. So then actually this will take 3 clock cycles to complete instead of 1 clock cycle. But each part will be much smaller than before. So in 1 clock cycle, you do this, and in the next clock cycle, this part, like that. So because for like setup, like timing requirements, we consider the behavior between two flip-flops. Like these two are independent. So because of that, we only have to consider the propagation delay of this part and this part and this part. So because we have broken down the circuit, then each propagation delay will be smaller. And then our setup time requirement will be fine because we are having a lower propagation delay. And if I explain that with my adder circuit, so here, so this is the original one, and the one improved one is we put registers between these, actually including all of these, all of the signals that are passing between these stages. We put registers. We are saving sort of saving intermediate outputs and using them in the next cycle instead of using everything in the same cycle. And so here you might think, so now instead of taking 1 cycle, it's taking 4 cycles. So this will be slower than before, even though we don't get setup time violation. But when we are doing it this way, we can also do pipelining. So pipelining is so because like only in a given cycle, if we only process one input, so in the first cycle only this part will be used. In the second cycle only this part, and like that. But so because the other parts of the circuit are unused, we can, and they are also sort of isolated by these registers. We can start processing the next input before the first one has completed. So in the first cycle, we are doing the first part of this, let's say A1 and B1. And then when A1 and B1 go to here, we will start processing A2 and B2, first part of A2 and B2. Then A1, like this. Then in the third cycle, we are processing A1 here, A2 here, and A3 here. So like that. So it will take 4 cycles for A1 output to get here. But immediately after that, we will get A2 in the next cycle, and in the next cycle, A3. So then the delay between like iterations is still 1 clock cycle. So the throughput will be the same. The latency will increase. But normally, in a lot of sort of processing systems, throughput is what matters, because then we can run like lots of iterations uh, without losing efficiency. So that's the thing I have done in this pipeline ladder. So here the logic is a little bit more complicated. Because you have to save a lot more things between registers when we are pipelining. But the behavior is like what I showed. So there are adders, like for 8-bit adders, and all of their inputs and outputs are coming from registers. Compared to this one, where like the cascaded RC adder. So all of these adders are using, they are not using registers here. So this module doesn't even have a clock. Like all of them are being done a SIG combination. Here we are using registers at every stage. I am not going to explain the code here, because I have to do the FPGA resources part also, and limited time. But the concept, all you have to know is the concept of like adding registers between them. These things, saving the intermediate output and using it in the next cycle. So then you will reduce so now the propagation delay will be reduced to the delay of 1 8-bit adder instead of all 4. So now I will take the pipeline adder and compile using that. And until that compiles, I will talk about hold time violations also. So these are, I said, like usually we have problems with something being too slow rather than being too fast. And in the rare case where hold time violation happens, it can be automatically fixed during implementation. So how it gets fixed is it will, the synthesizer will add a new additional buffer to this path. So buffer is like you give the input and the same thing will be the output. But it will also have some propagation delay. So we are artificially increasing the propagation delay by adding a buffer to that path to remove the hold time violation. Yeah, so here we can see that there are no setup time violations. The slack is positive, and we have a max of 247 megahertz because we broke down the long combinational path into several sections. And we can look at the worst case time paths, and none of them are failing, but you can see that one of the worst, like the slowest path here, it's starts from like it's between like one of the uh, it's within one of the adders. So we saved 2 to saved 3 means it's within this small. This is the only combination logic part that is causing a propagation delay. Like there are no delays between 2 8-bit adders because they are separated by resistor. So here there's no need to check the worst case paths really because there are no violations. So those are the common methods of fixing timing violations. If you ever get this kind of situation, the easier way is to use the clock divider. But if you are trying to make something efficient and you want to keep that efficiency, the proper way is to try pipeline. And so now let's go to the next part of FPGA resources. So here in this part, I will explain the different types of resources in the FPGA. Some of them are used in every design and some of them are sort of optional. And I will show how to check the resource utilization of a design also in quarters. And there are 2 components that might be useful to you, VRAMs and DSP. And I will show you how those can be used in your design. And if you have any questions, you can put in the chat. So the most basic thing in the FPGA are logic cells. So these are also called configurable logic blocks. So this is the basic component that FPGAs are made of. So it's what allows it to do various logical operations. So these consist of lookup tables and flip-flops. So lookup table is the component that implements combinational logic. So the reason it's called a lookup table is because so FPGA has to be customizable, right? So how the lookup table works is it defines. So if you give, so these are very small lookup tables, like maybe 6 bits or 4 bits. So it will encode it as, so if you give 0, so you can, so for any combinational circuit, you can make a truth table. So lookup table will sort of store the truth table of your circuit and give the output according to the inputs. So that is how the combinational logic is implemented. So these are all very small, and there are a very large number of lookup tables in FPGA. And flip-flops are the thing used for sequential logic. So the logic, a given logic cell, so includes some number of lookup tables and some number of flip-flops. Sometimes some reports will give the result as like number of logic cells. Others will give as lookup tables and flip-flops separately. That's why I use both terms here. So flip-flops also, there are a large number of them in the FPGA because like even if you want to store a 32-bit value, you will need 32 flip-flops. So the number increases very quickly. And LUTRAM is like, it's the same thing as lookup tables, but here it's used instead of doing sort of combination logic operation, it's sort of used to store data. So very small amounts of data. If we want to store then it's so corresponding to 0, you can store one value corresponding to one another value, like that. So basically it's repurposing lookup tables as memory, but only for small amounts of memory. So if you make an array in Verilog, it will be synthesized as this LUTRAM. If you don't specify anything special, like let's take something not like this is small. Yeah, this is a different design. I just so this is an array, multi-dimensional array defined in Verilog. So if you define something like this with size something larger, like maybe 60, it might be synthesized as a LUTRAM. So sometimes these are given as separate in the resource utilization report. This might be given separately, or it might be included in the LUT count. And the next thing is, so this is these logic cells, they will be used in any design that you make by default. So DSPs are something special. So they are specialized hardware unit that are made for math operations. So mainly, so things like multiplication and multiply and accumulate. So you can make multipliers using gates, basic gates, and gates or gates, and you can do multiplication like the way you do it by hand, by combining adders and basic multiplication logic. But that can use a large number of logic gates, and it might be slow. And also it might connected to our previous discussion, it might, because it's using a lot of gates, it might have a larger propagation delay. So DSP blocks are sort of customized for this type of operations. So it's a sort of circuit custom made for multiplication, so that it will have a smaller propagation delay that you can use for that type of operation. So it's normally used for various signal processing tasks like filtering, and also if you are making AI accelerator, it can be used for matrix multiplication. But it will all a single DSP won't be able to multiply an entire matrix. Like it will have sort of 4 bits or 8 bits, something like that. And the synthesizer will, if you want to multiply larger bit widths, the synthesizer will automatically connect multiple DSPs together for that. And because, so I said, if you try to make a multiplier from scratch, it will use a lot of sort of logic blocks. And that means if you might not have enough lot resources for other things that you can use for other things. So if by using DSPs for multiplications, you can save on lot utilization, and also you can avoid timing problems because DSPs will be faster. And block memory is also called BRAM. So this is a dedicated on-chip memory for storing large amounts of data. So I said the LUTRAM or distributed RAM is used for small amounts of data, like small arrays or register files. VRAM is used if you want to store large amounts of data. So there are multiple VRAMs in the FPGA fabric, and they are in units of either 18 kilobits or 36 kilobits. So if you want larger VRAMs, the synthesizer will connect multiple VRAMs together to get the size that you want. But there are sort of limited number of VRAMs in any FPGA. So for example, one that I worked with before, it has like 100,000 LUTs, 100,000 flip-flops, but only 150 block RAM. So it's more limited than other resources. And the use cases are, so if you are doing image processing, the images are usually large size, like in MBs sizes. So it will need if you try to use LUT RAM for it, then it will use up all of the LUTs available. So then you can use VRAMs or for large amounts of data. So in AI accelerators, you can store the weights and biases in VRAM. And in large 5.4s, you can also use VRAMs if the data stored in them is large. And VRAMs have a lot of customization. So you can change the data width of the VRAM to support. So if you want to take 64 values parallelly for some kind of accelerator, you can make a VRAM of size like that has a width of 64 times 8, something like that. And it has single and dual port access. So dual port, so if you want to read and write to the same VRAM at once, you can use dual port. And it can do multiple reads and multiple writes as well with 2 ports. So VRAM is an important thing we can use, like especially if we are going into something like image processing or AI acceleration, because otherwise you can't. It's not feasible to store everything that you need for the computations. So this is like an image of how different resources are placed in the FPGA. So CLP are the logic cells, and there are BRAMs and DSPs, and IOBs, like these are the connections to the input output pins. So there are pins on the, if you have seen FPGA board, there are pins, reset button, like buttons you can use for reset, LEDs, different things are there. And the PLLs are for clock synchronization, that type of thing. So this is how these wires, those are the routing resources. So because FPGAs are customizable, you can like configure like which of these wires are enabled so that you can connect circuits in very customizable ways. It's not restricted to a certain path. So resource utilization is important because like there are limited number of each of these resources in the FPGA. And if you use too much of them, obviously the synthesis tool won't be able to place all of this in the FPGA. But even if you don't exceed the amount of resources, like if you go very close to the maximum limit, then it might not be able to find a way to route between all of the components that you need. So it can allocate your logic to different parts of the FPGA. But if you try to route between them, like there are crossovers and like congestions, so it won't be able to route. Then still you won't be able to run it on the FPGA. So because of that, you have to think about resource utilization when making a design. And the amount of resources change depending on which FPGA you are using. Uh, so I will show the resource utilization report of the design that we synthesized just now. Here, so that is done on the analysis and synthesis. So that's the part where it will analyze all of the logic you have written and sort of allocate them to FPGA, various FPGA resources. So here we can go, it is also in the flow summary. So the location of these things are a bit different if we are using Vivado, but from there is a sort of menu like this one where you can find where to get the resource utilization report. So here logic elements means those logic cells containing lookup tables and flip-flops. So it says there are 22,000 of them in this FPGA. So this is the D0 Nano. And I have used 408 of them, so not even close to hitting the limit. Pins is the input-output ports that I'm using. Memory bits is the BRAM resources. So there are this much bits of BRAM memory available in this board. I'm only using 1 kilobits of them. So later I will show you how to use the BRAM in your design. Currently I have added one for this adder test module. That's what is showing up here. So a more detailed summary is available in this part. So I said the lots sort of lookup tables with it can have different number of inputs but very small number of inputs. So this is like four input truth table that is stored in the FPGA. So it gives details on how many LUTs are used in different configurations. And registers, it says how many registers are used. And memory bits are same as before. This is the BRAM resources. And embedded multiplier 9-bit elements means these are the DSP resources. So I haven't used DSPs here. There is no multipliers because this is the adder circuit. So this is the resources summary. And so if you want to see which of the modules are using the most resources, you can go to this. So this is the you can see the hierarchy of modules that you have made and the amount of resources by each one. So I will show this in detail. I have another more complicated design where I will show the resource utilization by entity. So RAM summary means this is the BRAM I have used. So those are the important parts of the resource utilization report. And now I will show how to, I think I will first show there's another design I wanted to show. So this is a more complicated design of a systolic array. So this is commonly used for matrix multiplication. So it's sort of a 2D array of multipliers. And we give one input matrix from this side, A, and another input matrix from this side. And so they get multiplied together. And then, so the addition is done. So we have to, for matrix multiplication, we have to multiply element wise and then add them together. So the adding part is done by this adder tree. So there are multiple adder trees. So then the output will be, this will be one row of the output, one row of the first matrix, column of the second matrix. It will be added, and then at each cycle, you will give a new row and a new column of the two matrices. It's a bit complicated, but search systolic arrays, like it's a very common thing that's used for uh, hardware acceleration, and there should be a lot of resources explaining that. So I'm just showing this too because it has a lot of multipliers. So I want to show how that appears for resource utilization. And if you look at the design, so this is the systolic array, and it has an array of multipliers and an array of adder trees. So, and I have parameterized the size of this. So currently this is a array of 4 by 4 multipliers, and it's adding two matrices with data of 8-bit width. So each element coming into these multipliers are 8-bit. So I will synthesize this one also. It will take more time because this is a more complicated design with lot more elements. So generally it will take more time to synthesize. But we can see the resource utilization at this step, analysis and synthesis. So this part we don't need to check the resource utilization. Uh, so here we have the resource usage. Here because we have used so to use DSP blocks. So I haven't done anything special here actually. So the multiplication is done in this PE module. So this is the part where multiplication is done, and I have just used the multiplication symbol in Verilog. And because there are DSPs available in the FPGA board, the synthesizer will automatically allocate a DSP for that. We don't have to do anything specially. But if let's say DSPs are limited, like we need to do more multiplications than the amount of DSP, then some of them might be synthesized as using like normal LUTs. That all depends on the uh, resource availability of the board. But to use DSPs, you don't have to do anything special unless like there are very large number of multiplication. So here you can see that DSPs have been automatically allocated for this. So there are 4 by 4 multipliers. So there are 16 DSPs used. And the other resources are similar to before. And you can check resource utilization by entity. So suppose you are overusing resources, then you want to track down which of these submodules are causing the problem. And so here it will give a hierarchical breakdown of that. So there are 4 adder trees. Each of them are using 24 LUTs. So most of the LUTs are actually used by the multiplier array. So multiplier array, yeah, so the multiplier array has a bit of logic to check whether to load the second input. So that logic is like replicated across all of the 16 multipliers. So because of that, it's using some amount of flux, and there are 16 of it. And you can do the same analysis for logic registers. And DSP elements, you can see it's only being used by the multiplier array, not by the adder trees. And there are DSPs of different sizes, 9-bit and 18-bit. So because our multiplications are 8-bit, it's using the 9 by 9 DSD. And I will show you also, like, so I have made it size 4 by 4. So how much can we scale this up before uh, with the under the resource? So if I make it 8, so previously we have like 350 LUTs. If we synthesize this again, so now because this is a 2D array, it will be scaled a lot. Like now there are 64 multiplier units. So we might get unexpectedly large resource utilization. So when we are making something like this, so more parallelism is better. So that parallelism means you can multiply more larger matrices faster. But there's a trade-off between how much resources we are using and the speed that we can get. So we can make larger and larger multiplier arrays, but then we will hit a limit where we have run out of resources in the FPGA. So here, this design is actually not complete, and like if you are running this in a FPGA, this input and output should be uh, provided by a block RAM or something like that. So it shouldn't be exposed to the outside because otherwise we will have to assign them to input pins. And this error is giving that there are not enough IO pins available on the board. But I think because analysis and synthesis has completed, we can still check the resource usage. So previously it was 350, now it's like almost 2000 logic elements used. Sorry, this is the LUTs, almost 1500. So it has increased a lot. And because there are more adder trees as well now, and they have to add more inputs together. So they are using more logic. And the multiplier arrays are also like there are 64 of them instead of 60. So they are using more LUTs as well. And there are 64 DSP elements used. So here you can see a breakdown of all the results that are used. And this breakdown is useful for hunting down which modules are overusing resources if you are trying to reduce it. So if you want to, for example, in this case, if you want to reduce the LUT usage, uh, if you try to read, so this is each PE is using 16 LUTs. So if you reduce this to like 14, that will actually cause a large decrease here because there are 64 repeated P's. If you somehow manage to make this slightly more efficient, that can cause a more larger change in the resource utilization than if you like focus on one of these other trees. So you can look at it that way when you are trying to optimize resources. So here, if we look at the total, so we are using more of the total logic elements now. So, but there are still more available, so we could make that array even larger. But I'm not going to do that now because when the design gets larger, it will also take more time to compile. So that's about resource utilization. And finally, I will show how to use block RAMs in your design. So here in this example, I have used a VRAM to store several different test inputs so that you can, so normally if you are simulating, you can give any input that you want from a test bench. But if you are running in FPGA, like actually running it on the FPGA, normally you might be limited by the input you can give by switches and buttons. But if you use a VRAM, you can store some predetermined inputs in the VRAM and then feed them into the your module that you're testing at every clock cycle. So that's what this adder test module is doing. And it's storing inputs in the VRAM. It's giving that to the adder module and taking back the adder module output and saving it to the VRAM as well. So I will show you how to make this kind of VRAM in your design. So you have to use the IP catalog. This is the IP catalog. And you can search for block memory. You might have to search here, like on chip memory. The RAM is the VRAM. So we can use a single port or dual port. So here for my use case, I'm doing both reading and writing, reading the input and writing back the output. So I'm using a 2-port RAM. So you can double click that. And IP variation name, you can give any name. I'm calling it VRAM 2 because I already have one named VRAM here. So then you will get a window to customize this VRAM. So this is sort of the input output interface of this one. We have data. So first of all, we have a clock. So VRAM operates with the clock. Like you can give an address, and it will give the in the read port. It will give the output as the data stored at that address. And you can also give a write address and some write data. And at the next clock edge, it will store the that given data at the given address. So that's basically how the VRAM works. And you can, so there are some options. You can use the dual port RAM with one read port and one write port, or you can use both ports for both reading and writing. So here that's a more complicated interface then. There are two read outputs as well. So for this one, I'm using one read port and one write port. But if you, let's say you want to, so there are two modules that you want to test at the same time. Then you can use two read-write ports, and you can use those ports independently of each other. And so memory size specified as number of words. Then it's better to choose this one first. So data input bus B. So this is asking how wide should the VRAM be? So how much data in one row of the memory. So I'm giving it as 8 bits. So if you want to do something, so let's take this historic array example. If you want to, like if the width of this is 8 and each of the inputs are also 8, and you want to give inputs parallelly to all of these, you can have a 64-bit with VRAM. So you are not limited to like traditional sizes. So you can make the data bus with 64 if you want. But here I'm just using 8, yeah, because I'm using it for the adder module. So that one is a 32-bit adder. So I'm using one input as 32 bits. So now it asks how many 32-bit words of memory. So that means what is the depth of the VRAM. So how many rows are there we can store data. I'm giving just 32 rows. So then this one you can keep it as auto. And single clock, no need to use separate clocks for read and write. We only have one clock. And if you want, you can make a read enable signal, but that means you have to give the read address and also read enable to get the output. But for read operation, normally we don't really need that. Byte enable means you can edit like one byte at a time of the, so even though the one row is 32 bits, you can edit you can update or read 8-bit sections. So in this application, I don't need that one either. And which ports should be registered. So this means a VRAM will always take at least one cycle delay to give the output. So if you give the read address and the um, yeah read address in the at the next clock edge, it will give the read output. So this is asking whether we need an additional output register. So it shows this clearly. So there is already a register small flip-flop at the input. If you so if you keep it like this, will be only one cycle delay before the output. If we add two registers, so we have this then there will be two cycles of delay before we get the read out. So if we this is you might be wondering why this is needed. So this is used for same purpose as we discussed pipelining earlier. So if there are timing violations and you need to reduce the combinational path, then you also if you find out that this section has a large delay, then you can add another register to break up that path. So that's the use of this read port register. But normally you don't need that, and it's a bit annoying to deal with two cycle delay when we are implementing the using the VRAM data. Clock enable signals are also not needed. Um, this is asking whether what should you do if there's a read, if you are reading and writing at the same address at the same cycle. So I'm giving it as make it output the old memory content. So even though the write is trying to update it, the read should give the old one if it's happening within the same cycle. You can define it according to your requirement. Uh, and do you want to specify the initial content of the memory? So this is important if you are trying to use it as a test module like I am. So we can give a pre-computed list of inputs to store in the DRAM. So I already have a file for this. Uh, so the file is this init.hex. So there is a format for this file. So if you don't have a file like this, there is a way to create it from the Quartus interface also. I will just put it here for now and show you the file format later. And this is so when you are simulating with VRAMs, you will need to include an additional library. So I will try to. There's not much time left, but I will try to quickly show that as well. And this is what asking what files you want to generate. So I am taking this instantiation template also because it will show what is the interface of this VRAM so that we can use it in our design. So now this VRAM is created and you can see how you can use it by opening this .v file. So this has the names of the input ports and the width of the input ports. So you can use this as a normal module now. So I have used this DRAM.v, is the one I generated earlier. I have used this inside this adder test module, just like defining the normal module, but you are using the port names defined in this one and making sure that the port widths are the same as this. So after you generate the VRAM, you can use it like a normal module. And the process, like maybe the settings of the VRAM might be a bit different in Vivado, but it has the same basic settings as this one. And here also, like it can also be used as a module. And the VRAM, like port names and stuff, can be different between them. So always make sure to check the generated Verilog file to find out the port names. So that's how to make the VRAM. So I will show that hex file also. I will add it to the if you haven't made a hex file, you can do it using new, like memory files, hexadecimal file. So I will go with the VRAM size I used before, word size 32, number of words 32. Now it has like this is the data you want to fill in the VRAM. So there are 32, yeah, there are 32 addresses. Each of this we can fill it with the 32-bit value. You can use any value. You can use any value and save this file somewhere. I will add the one that I also. So this is the init file that I added to the VRAM. So it has sort of formatted itself differently, but I have given sort of pairs of A and B data here to be used for testing. And this init file means like when the FPGA, when the design is loaded into the FPGA, the VRAM will be initialized with the contents of this file that we have given. So that's useful for giving like larger number of inputs instead of like being limited to switches and buttons when you are running something on the FPGA. And in Quartus, there is also a way to weave this contents of the VRAM in real time while you are running. Um, I will be able to show that today, but there are resources on the internet about how to do that. It's not available in Vivado, only in Quartus. So I will also quickly show, also there is something you need to keep in mind. So if you want to edit this VRAM properties after you have created it, you can go to the IP components view and right click editing parameter editor. And here you can go through all of these settings and change anything if you need. What I want to say is, so previously I selected the file from here and it gave a relative file path. But the problem is if we are going to simulate this design, the simulation starts from a different folder. So it will give an error that it can't find this file. So it's better to give the full file path here so that both the simulation and the synthesis can find this file. That's something that doesn't happen automatically, but keep that in mind. So I will show how to run simulation with the VRAM. So I have a simulation file called top TB that is used for this. I haven't put it in the files here. I will add it in the model sim simulator. That can be accessed with run simulate tool. So again, simulation is a bit different in Vivado, and there is no special thing you need to do for BRAM in Vivado simulation. It will just work. Only Quartus has this special thing we need to do. So here I will go to compile and add the test bench. And then go to simulate, start simulation. And here there is a tab called libraries. So here the library used for VRAM is uh, yeah, this Altera MF where is the one that you need to use when you're simulating VRAMs. It's not clearly explained why. So when you are making the VRAM, it will say that the libraries that, so go to the properties. So here it says Altera MF is the library that you need to simulate it, but actually you need this one, Altera MF. It's not clearly explained why, but you can use that. And then you can go to the design tab again and select the test bench and click OK. Then it's like normal, the way you do simulation. And you can run the simulation. So then it will run as normal. So if you don't add that library, it will throw an error saying that it can't find the VRAM module. So that's how to use the VRAM. So the VRAMs are useful, especially so either for something like this, you need to give some test data. So you, uh, for example, another one is if you are doing the processor design project. So you can store a program in a VRAM and give it when use it when running on the FPGA. And in Quartus, there's an added benefit of being able to see the VRAM contents and change them in a real time. Otherwise, if you are doing something like this, like making matrix multipliers, something like hardware accelerators, then you will have like large images that you are giving to the matrix multiplier. Then you can use VRAMs to store that. Otherwise, it other distributed RAM won't be large enough. So hope I think it will be helpful when you are doing more complex designs. So those are the things that I want to cover, and I hope things were clear. Like I tried to make it easy to understand for different levels, and some of you might already know some of these things, but I hope these things were important for you to make, like try making real designs in FPGA and to try out more complex things. So if you have any questions, you can ask. Yeah, if you don't have questions, I think we can end the session.
Thank you, Ms. Anuki, for that insightful session. I think everyone here got a much clearer idea and understanding about FPGA resources and timing analysis, how it actually comes into play when building real systems. And I think it's a little less scary now as it was before. And of course, thank you to everyone who joined with us today and stayed engaged throughout the session. And Ms. Anuki, we really loved hearing about those concepts from an industry perspective, and we truly appreciate you taking your time to share your knowledge and experience with us. We hope to see you all in our upcoming sessions. Until then, keep exploring, keep building, and keep pushing your boundaries. Have a great evening, everyone. Thank you.
Thank you.